The final talk before we take a short break by Justin Spilker from Texas, who will tell us about molecular outflows. So Justin, please share your screen. You already shared it. Thank you.
Okay. Does that show up okay?
Yep.
Okay, great. Yes, my name is Justin Spilker. I'm a Hubble Fellow here at the University of Texas. I'm very glad to have the electricity to be able to bring this talk to you today. I'm glad this workshop is this week and not last week, for sure. So I want to talk today about the first sample that we've built up over the past few years of molecular outflows in the very distant universe. These results are based on a couple of papers that you can see referenced there at the bottom. And all the data and tables and everything from the papers are available on our collaboration website. And so this was a project that was really kind of inspired by the realization over the past 10 to 15 years that things like feedback and outflows are really essential for the way that galaxies form and evolve. So I don't have a lot of time to go into all the ways that feedback and outflows influence galaxies, but it ends up being this really sort of tentacle scenario where the feedback influences a huge range of observables, a huge range of properties of galaxies, all the way from the way that they inhabit dark matter halos to the way that their metal contents evolve with time. Feedback connects black holes to the galaxies that they live in and sets the overall efficiency of star formation. And so it ends up being really critical to sort of understand how this feedback impacts the galaxies that we observe across the universe. And in particular, since stars form out of molecular gas, the impacts that feedback has on the molecular gas ends up being quite important for the way that they evolve over the long term. So for example, if you want to make a quiescent galaxy, you probably need to be able to keep that galaxy from having molecular gas that it would otherwise turn into stars. And even way early into the history of the universe, we know that that feedback must have been operating. This is just one example of a very massive galaxy that we know existed at as early as redshift 4. The stellar mass is about 10 to the 11 solar masses. And if you don't speak optical spectroscopy like myself, you can tell that this galaxy is quiescent because of the label here on this upper image that tells you that it's quiescent. And if you basically just do some quick math, divide the mass by a star formation rate in order to form this amount of mass by redshift 4, you find that the star formation rate that you would need to form a galaxy like this is much, much higher than the typical sort of star formation rates that you get from UV bright galaxies in things like the HST deep fields. And so what that basically tells us is that the sort of typical galaxies that you might see in an HST image are not the ones that are forming these really massive early quiescent galaxies. And instead, it's probably coming from galaxies that are much more dust obscured. And so they don't tend to show up in the small area surveys from things like Hubble. And this has been sort of speculated about for a long time now, actually. For a lot of reasons, we think that dusty galaxies are probably the progenitors of these earliest quiescent galaxies. Just in terms of their star formation rates, their masses, the dark matter halos that they live in. All of these sorts of circumstantial lines of evidence point towards the fact that these galaxies, these really dusty galaxies, are probably going to become the first generation of quiescent objects. And so I'm just going to sort of assert that if that's true, we can use these very distant dusty galaxies as, I guess you would call them, laboratories for the way that feedback operates in the early universe. And the basic reason for that is just because if these galaxies are going to form stars very quickly and then stop all the way by redshift 4, some physical process or processes have to be in effect to basically prevent that star formation from resuming, at least in the short term. And so the sample that I'm going to use for this, just to cut 5 years of work down to one slide, is coming from the South Pole Telescope survey, which surveyed a huge area of the southern sky. And from that, we have assembled a sample of about 100 galaxies that all have spectroscopic redshifts. And by virtue of being bright, they all basically all happen to also be gravitationally lensed. And so this is great because now with all of these redshifts, we can go and basically pick any spectral line that we want in order to study this sample in whatever way you might desire. And the lensing also ends up benefiting us because it means that we can get higher spatial resolution than you would otherwise be able to get, similar to Seju's talk that he just gave 15 minutes ago. And so to study the properties of feedback here, the observational tracer that I want to use is going to be this molecule called OH. hydroxyl. There are a lot of reasons that this is a really great tracer of molecular outflows in particular. It's a really simple molecule. It's easy to form. The abundance is high. The transitions are really strong. And we have a long history of observations of these lines of OH with Herschel in the local universe. So it's just a really nice, easy built-in comparison sample. And so the signature that we're looking for here is this blue shifted line wing. So this is basically the fact that you're seeing this line in absorption tells you that the gas is in front of the galaxy. The fact that it's blue shifted tells you that it's moving towards you. And so the fact that you can combine those two, little pieces of information tells you that these must be outflowing. This must be outflowing gas. And so I'm targeting a sample of about 11 galaxies from this SPT survey from redshift 4 to 11. It still ends up being fairly high frequency observations, so it took ALMA a little while to build up a nice size sample. This ended up being several years of observations in order to line up the good weather season with the right array configurations for ALMA. But now that it's done, we have a nice sample of about a dozen galaxies with these observations of OH. And so just to sort of cut to the quick, here are all the OH spectra from the entire sample. OH happens to be a doublet, so every time you see one absorption line, you actually see two, which is why most of these absorption lines are double peaked or double troughed rather. And what you see is that in many of these cases, we actually see these really strong blue shifted line wings. For example, this one down here in the lower center, we don't even get all the way back up to the continuum level after 1,000 kilometers per second of bandwidth. And so if I go through and carefully sort of classify which ones of these have outflows and which ones don't, we wind up finding that a huge fraction of them have outflows. There's something like 3/4 of the sample. And so since we're seeing this in absorption, what this tells you is that A, the outflow rate, just in terms of the occurrence rate, has to be very high. And B, the covering fraction or opening angle has to be very high as well, because otherwise you wouldn't be able to detect an outflow in absorption towards such a high fraction of the sample. So people always ask me about the outflow rates. And so here I've just sort of assembled the biggest sample that I could find of outflow rates in the low redshift universe. These circles are all objects that were also observed in OH, and the squares are objects that were observed in CO. And so if I throw our redshift 4 sample on here, we found that basically they have very high outflow rates. This probably isn't all that surprising because these are among the most highly star-forming galaxies in the entire universe. And so you would probably expect that they should have high outflow rates. What might be a little unexpected is that the loading factors, in other words, the outflow rate divided by the star formation rate, are a little less than 1. So basically these galaxies are growing faster than they're able to expel the gas. And this is maybe a little bit surprising compared to similarly highly star-forming galaxies in the local universe. But one issue, I think, is that these outflow rates and the energetics of these outflows are really highly uncertain. I'm giving you these outflow rates, but there's a lot of assumptions that go into this as far as the geometry is concerned, as far as the abundance of molecules is concerned, and so on. And there's not really a whole lot of ways to get around this, to be honest. At least for the next several decades, we're going to need some sort of new facility that will give us a better chance to constrain these outflow rates. So even in a case where I've observed the outflows directly, I'm not even trying to infer what the outflow rates might have been based on other indirect tracers like, mass or metallicity or any of these sorts of things. I'm still not super confident that we're getting these outflow rates correct to within a factor of 2 to 5 at best. And so I'm actually going to argue that one better way to constrain outflows and feedback in simulations is actually going to come from the structure of outflows themselves. And so I'm just showing here 2 different simulations of outflows. On the left, the molecular gas in outflows winds up only surviving in these really small chunks. So basically anywhere where the yellow gas here on the left has survived into the outflow, the molecular gas, it winds up being in these sort of 100-ish parsec sized clumps, but there aren't very many of those clumps. On the other hand, on the right, the molecular gas sort of reforms out of the hotter material as the outflow sort of expands. And in that case, we basically will have no hope ever of resolving the structures in these outflows because they wind up on scales of about 10 parsecs. And that's just not really feasible to resolve with any realistic facility in the near future, or even the distant future for that matter. And so the point is that the details of how feedback is implemented in these simulations lead to really large differences in the structure of the outflows. And because we have a lens sample, this is something that we can actually constrain. After a lot of math and work, we can reconstruct the intrinsic structure of what these outflows look like. And so here's just one example of a galaxy at redshift 5.3. The continuum emission from the dust is pretty smooth. We don't really see any signs of structure there on scales of a few hundred parsecs.
2 minutes left.
Yep, thanks. But what's cool is that on the left here, the outflow absorption, this is separating out only the emission or only the absorption that is definitely in the outflow, shows this kind of clumpy structure where we see a few different clumps separated by a few hundred parsecs. And that's actually ubiquitous amongst the sample. So here's just the gallery of all of the targets where we detected outflows. And you can see that these clumpy structures are really common, actually. And so I can tell you that it looks like we are not in sort of a spherical cow kind of scenario where these outflows are just sort of propagating, sort of uniformly in a spherical fashion. It looks like it's a really highly clumped structure. And so I can tell you that these outflows look like they're clumpy, but the resolution of the data that we have now doesn't actually let me constrain the size of the clumps themselves. So in other words, I can tell you that there are multiple clumps, but I can't tell you how big those clumps are. But to sort of boil down an argument that took a few pages of the paper, from optical depth arguments, I can sort of predict that in order to resolve the clumps directly, we're going to need to reach resolutions of about 50 to 100 parsecs. And that might sound crazy, given the typical size scale of galaxies in the distant universe, but this is actually achievable in the distant universe with lensing. This is only about 2 to 3 times higher spatial resolution than the data that we already have. And so it's actually possible, I think, to get down to these really, really fine spatial scales in the very early universe to figure out the structure of outflows. And I think it's going to be a really powerful tool. So just to summarize, this is the first sample of molecular outflows in the very early universe. We found outflows in a huge fraction of the sample, which is good. So if you are out there in the audience sitting on samples of galaxies that seem like this might be viable, it doesn't take a very large number of galaxies to probably convince yourself that just by luck you'll have at least a few outflows. They look clumpy on scales of a few hundred parsecs, but I can't actually tell you what the size of the clumps are at this point. And I think the sort of interesting idea is that it might be more useful to constrain simulations with the structure of outflows than the actual outflow rates or energetics themselves. So I'll stop there. Thanks.
Yeah, thanks a lot, Justin. And nice allusion to Seiji's talk about how to achieve the high resolution. So there's time for a question. I'll skip my own and go to Ilseng. You already had one. I go to Chen Tao maybe, who asks, in one of the spectral plots, the OH absorption seems to have a redshifted component. Is that an inflow?
Yeah, so you're right. So Chen Tao's right. If in theory, in principle, you can also use this line to trace inflows. In that case, you'd be looking for red-shifted absorption instead of blue-shifted. I'm not convinced that any of these actually show inflow. We didn't set up the observations, right? ALMA has a limited bandwidth, so I'm showing you basically the entire velocity coverage that we have. So I didn't set up the observations to have a really good coverage of the red-shifted side of the line profiles. A few of them, for example, this one up here in the top row, looks like the OH is peaking towards the redshifted side. But I think the key issue with the interpretation of this actually comes from having knowledge of what the C+ line is doing. So in this case, you actually see that the C+ is double peaked. And so probably this galaxy is just a merger. And so this is kind of the dirty laundry bit of interpreting absorption lines in the high redshift universe, is that the galaxies themselves are pretty complicated in terms of their kinematics. And so when I classify things as outflows, I'm only picking them as outflows if they're more blue shifted than any of the emission that I can see. And so in this case, for example, even though this line profile is slightly redshifted, that could mean that it's outflowing from one component of a merger. It could be inflowing towards the other component, or it could just be systemic absorption coming from the interaction region. So for example, if you look at the antennae galaxies in the nearby universe, most of the emission, most of the action is coming from the area where those galaxies are crashing into each other. And so I'm not claiming any inflow here, although in principle, yes, it is possible that you could use this line to do that. I think you would just want to pick a sample of galaxies that's less complicated in terms of what their kinematics look like.
Okay, interesting. Cool, thanks a lot. So there are several more questions in the thread that you can answer